Okay, this is Unit 3 of CSC270. And in this unit, we're going to look at analog signals. So analog signals are the voltages that are not discrete. They're not either 0 or 5 volt, but they can be anything in between. And the Arduino limits itself to the range 0 to 5 volts. It will not be able to measure anything greater than 5 volts. But we have ways around that if we had to deal with something that is larger. The other thing that we learned from the documentation is that all the analog to digital converters inside the Arduino, these little devices that will look at the voltage and translate that into a number, that's what an analog to digital converter is, their accuracy is 10 bits. So basically they look at the voltage between 0 and 5 that they're measuring, and they divide the whole space between 0 and 5 in 2 to the 10 bits, that's 1024 discrete values. So 10 bits for us means that 2 to the 10 equals 1024. The space between 0 and 5 volt, which I have here, is going to be divided into small bins, 1024 different bins. So that's basically 5 volts divided by 1000. That's how big each one is. So it's very fine kind of accuracy that the Arduino has. And when it's going to measure a voltage, say let's assume that it's measuring something like, so what does that look like? Maybe I would say this is like 3.2 volts. So what the Arduino is going to do is going to do kind of a rule. This particular line that I have here, let's assume that it's really 3.2 volts. So what number will the Arduino return to us? Well, it's going to be, if there's 1024 in 5 volts, if I only have 3.2 volts, that's going to be, and I've just done that on the computer, 655. So that would be the number that it would return. So we're not going to be measuring, so we're not going to get the actual float number, a real number, that is the voltage. We're going to get a number between 0 and 1024, knowing that 0 corresponds to 0 volt, 1023 corresponds to 5 volt, and anything in between is linearly computed as that. All right, so 3.2 volts would correspond to 655, and that's how we would compute that. So how do we program that? Well, fairly simply. We cannot use the digital pins that we were using before. We have to use analog pins, and there's several of them, 15 actually, for us available, and they're labeled A0 through A14. And if I bring my video here, what I'm going to see, I'm going to make this bigger. So that's where the analog pins are, right here. And you see that I'm already using one of them here, A7, right? Sorry, right down here. I'm using one already right here. Okay. So these are the analog pins. So that's what I'm going to be using on my Arduino. So how do I program that? Let's go back to that. So here in this sketch, I'm using A3 as an analog pin, so I'm declaring a variable to have that name. I'm going to be reading something from that pin, so I want to store it in some kind of value. So, and I'm going to be displaying on a serial monitor, so I have to initialize the communication speed here for my serial monitor. And then val equals analog read. That's a new function. I'm going to read the pin, analog pin, with an analog reading function, which is orange coded. And then once I have that, then I'm going to print it on the serial monitor. All right, so let's play with that. I'm going to go to my Arduino sketches, and potentiometer is the sketch that I'm going to be using. I've added a delay so it doesn't print too fast. And so here is how I have, so let's go back to QuickTime here to see how I wired up the potentiometer. So that's the potentiometer, and I've wired it so that all 3 pins are in different columns. So the 2 pins that are together, I'm going to connect one of the pins to +5 and one of the pins to ground. Okay, and so that's a resistor, and by turning that little knob at the top, what I'm doing is that I'm making a little piece of metal go in between the so this is a resistor that is around here, and by turning the knob I'm going to change the resistor. So the middle point here will be connected to this orange wire, and that's the one that goes to the analog pin. So the analog goes to the middle, and the other 2 go to +5 and ground. And then by turning this, I should be able to make the numbers change. So let's bring up the sketch again. I'm going to move it right here. I'm going to open the serial monitor, and I'm going to download the sketch. And as soon as it starts, here it's displaying some number. And I'm going to be, let's see if we can see both of them. That'd be cool. All right, so I'm going to change this. So see, by turning to the right, I'm decreasing the numbers. Should be able to go all the way down to 0 or close. So that's one thing we're going to see here. Is it's not going to be very precise, and that's typical of potentiometers. And even by just not even changing the value, not even turning it, but just moving it around, I'm going to get different numbers. That's typical. That's normal. If you've ever played with a joystick, and programmed, read the joystick value with a program, you probably discovered that these numbers jump quite a bit. That's also something you do in robotics. You play with all devices like this, and you see I'm trying to go all the way up to the largest, and you see that it oscillates between 1022, 1023, 1020. That's normal. There's some slight variations here, but that's to be expected. So, so whenever we're going to be testing for particular values, we're going to test within range. If what we're reading from the potentiometer is between, say, 990 and 1023, then we'll know that it's high. So we'll just use ranges of values rather than we're not going to try to get the absolute exact value. So that's the way it's going to work out. All right, so that's for that. Let's continue. So what particular devices will generate voltages for us that we can use, set like the potentiometer? Well, thermistors are resistors. Like the potentiometer is a resistor that we can mechanically change. The thermistor is a resistor whose value changes with temperature. So depending on the temperature, its value is going to change, and we're going to have a very similar setup as the one that I have here. Potentiometer, yes, we just did that. Joystick, a joystick is 2 potentiometers to measure whether something is moving this way or that way. So it has 2 potentiometers inside. Pressure sensor, so something that is going to be sensitive to pressure, and so depending on the weight on the sensor, you're going to get different numbers, and you should be able to measure weights in that way. Light sensor, it's a resistor, so you see all of these are kind of resistors whose value changes with something happening. So light sensor, depending on the amount of light, your resistance is going to change. And then battery check, just quickly, I had mentioned that in a previous unit, if you want to measure whether your 9-volt battery is good or not, you could have the Arduino measure the battery voltage using an analog input pin. The little trick here is that we just saw that the analog input pins measure voltages between 0 and 5 volt. If we use a 9 volt battery, then we have to play a little trick, and this is the trick we're going to play. Let's assume that this is our 9 volt battery. There's a plus and a minus. That's the ground, the same ground. I'm going to connect the minus of the battery to the ground of the Arduino. That's my Arduino. Okay, and I'm not going to connect the plus, the 9 volt to the input pin, so I'm going to use one analog input pin. But I'm not going to connect these two together because 9 volt is greater than 5. But what I can do is that I can divide 9 volt. I can use two resistors like this, and I'm going to make them the same value, say 1K and 1K. And so I'm going to connect this to the Arduino, so that's the ground of the Arduino. So what do the 1K and the 1K, what do they do? Well, if you apply Ohm's law, which we have done in the past, you will see that if my battery is perfectly fine, then the voltage I'm going to have here is going to be 4.5 volts. It's going to be exactly half. And 4.5 is less than 5 volts. So I should be able to do some testing with a brand new battery and see what kind of number my Arduino is going to measure on the input pin. So 1024 correspond to 5 volts. If I have 4.5 volts, that's the number that I should get. It's 921 roughly. So I will know that my battery is going to be good if the Arduino reads a number in the order of 921. And if it's 900, it's probably fine. We know that 60%, if a battery is less than 60% of its nominal value, it's dead. So we can do some testing, but that would be how we would do it. So so this is how we're going to connect our potentiometer, and I've taken this from one of the tutorials, and you'll see that during the lab. They're very nicely illustrated here, and you can see exactly how to connect things together. This is the old Arduino right here. This is the old one, but similarly for the Elegoo that we have, Elegoo kit, it should work similarly. So, and by the way, Fritzing, which is one of the apps for drawing circuits, supports the Arduino. So you can draw something like this fairly easily with Fritzing, which is at the bottom of the schedule page for our class. Analog output. So here the Arduino cheats. It is not going to output a voltage that is between 0 and 5 volt. It's going to output either 0 or 5. That's the only thing it can do. But it's going to do that by outputting a signal that oscillates pretty fast, 400 and some hertz, and by outputting a pulse that is going to vary in length, it will be able to generate kind of an average value of a voltage that is going to be between 0 and 5. So this is a fake analog output. It's done by using pulse with modulation. And we can use pins 2 to 13 or 44 to 46 to do that. These are pins that have a little oscillator and that are going to generate a square waveform. So I have several examples here. 1, 2, 3, 4. These are 6 different examples. So we could output, so see this is a constant 0. If the output is zero all the time, so that's called a 0% duty cycle. The waveform is on 0% of the time. So that's, outputting a 0 volt. However, we could have something like this where the output is on a tiny bit of the time, something like 10% of the time. Okay, so, and if we do that very, very fast, and we connect that to an LED, we're going to see that the LED is going to be typically 10% as bright as when it would be on full on. And so I guess you understand what's going on here. So this is a 25% duty cycle waveform. And 50% means that half of the time it's on, half of the time it's off. So if we were to connect that to an LED, so we wouldn't see its oscillation, we would see the average light, and the average would be typically half what a bright, fully on LED would be. All right, so how can that work? Well, the example here is that if we were to use that through some driver, through some electronics, and connect that to a fan, this is how, this is my analogy, if you want. So let's assume that I have a fan that can be completely on or completely off, and I have a ball here that is fairly light and an incline, and I'd like the fan to push the ball up that incline. So if the fan is off, the ball is at the bottom. And then if I decide to turn on the fan, so suddenly there's air that is going through, and the air, you guess, is going to push my little red ball here up the incline, and so it's going to start going. And if I've no way of controlling the fan and I've turned it on full blast, then what's going to happen is that the ball is going to, very likely there's going to be too much air for my little red ball, and then it's going to fall off, right? So that's the problem. And if what I really want, I'd like to have a system where, and I could have some kind of sensor that detects where the ball is. I'd like the ball to stop like right here in the middle. So I'd like the fan to be gentle enough to push the ball up, say halfway, and the pressure to be just right so that the ball stays there. So one way to do that would be to use pulse width modulation, where I would very quickly, so maybe several times a second, several hundred times a second, I would send little pulses to the motor so that it would not turn with the maximum speed. So I could modulate the speed that way. So by doing that and adjusting the width of that pulse, I should be able to generate enough wind here to keep the ball stable right here. So that's the idea of pulse width modulation. So there's, you have to imagine there's going to be some averaging taking place. So the Arduino is cheating by sending a signal that is high and low, but it oscillates between the two very, very fast, hoping that whatever device is receiving that is going to kind of average out the value. So if my pulse width modulation is 10%, if my duty cycle is 10%, then the device is going to get 10% of the full power that I could generate. All right, so pulse width modulation pins, 3, 5, 6, 10, 9, 10, and 11. And so this is how this will work. By the way, the frequency at which the pulse width modulation is going to work is 490 hertz. So that means that there will be 490 pulses in 1 second. Okay, so that's pretty fast. So definitely for human beings, it's something that we cannot discern. We cannot see the influence. So if I want a 0%, this is what doing 0%, I'm going to send a 0 on a particular pin. So here I decided to use pin 3. If I want a 25% duty cycle, and there's a table of that, so the Arduino has tables to explain what particular duty cycle is associated with what number. So 25% duty cycle, 64. If I want 50% duty cycle, 127, 75%, 191, and 100% duty cycle, I would have to send 255. So for those of you who remember enough of the assembly language class, 255, if you have the maximum number for 100% is 255, means that we're probably using 8 bits, a byte, to define the value of the duty cycle. So 100% duty cycle will correspond to 255. That's a byte. We're using 8 bits to store the value that is going to be used for that. Something that I want to mention here, we don't need, when you're going to use pulse width modulation, you don't need to indicate in the setup function that we're using that on a particular pin. You can just directly use the pin and set an analog write. So that's the function we're going to be using, analog write, to output a number to that pin. You don't have to specify that you're going to use that pin as a pulse width modulation. I'm not sure why, it's a feature of the Arduino. All right, where is that? So here is a sketch where you'll look at it, try to figure out what's going on. I'm going to read something from the potentiometer on an analog input pin, and I'm going to translate that into, and I know that the maximum value that the potentiometer is going to give me is a number between 0 and 1023 included. And I'm going to transform that into a number between 0 and 256. I'm going to divide by 4. So whatever the potentiometer is doing, I'm going to send that to an LED that is connected to a pulse width modulation pin. So I should be able to adjust the intensity of the LED using this way. So that's what that sketch does. Take a look at it, verify that that makes sense. And you'll have to do that in the lab. All right. So the pulse width modulation, so we'll do that offline. I'll do that in an extra. I need a scope, so I need to change my setup. So here, the challenge scope later, but we'll do that. All right, so that's now computer science. I wanted you to see something that is important, that is an important concept in computer science, is that software and hardware, they are interchangeable. So remember that in the first half of this course, we've implemented finite state machines with flip-flops. And so here is an example of a state diagram that would require 2 flip-flops. It has 4 states. So I need 2 flip-flops, 2 bits, to store the value of the state. And here I see that there's an outside switch that controls it, and depending on whether the switch is 0 or 1, so I'm going to guess here if the switch is 0, I'm staying in the state that I'm in, but if the switch is 1, I'm changing state. All right. So it takes a whole analysis and gates and all kinds of hardware to make this work, and once it's designed and built, that's it. You cannot really change the behavior. You have a switch, you have your 2 flip-flops, and then some extra circuits, and that implements your finite state machine. With an Arduino, the finite state machine is going to be implemented in software. And so all you have to do is you have to have an outside switch, which is right here. Actually, I'm going to use a felt tip. I can use a resistor, my own resistor. I can use the one that is on the board as a pull-up. So here I'm showing that I'm using my own resistor. And then I'll have to connect 2 LEDs. So that would be 1 LED so that I can indicate which state I'm in. So I haven't shown that. I'm going to illustrate this because I have it done. So I'm going to bring this window back on, and I'm going to use a different sketch for that, which is called finite state machine. I don't need this anymore. So I'm going to download it here in my device. And so I've cheated somewhat. Where is my switch? It's right here. So so my 2 LEDs, green and red here, define which particular state I'm in. And whenever the switch, so that's, you know, instead of having a switch, I've just decided to have a wire that I connect to VCC or ground, and it's connected to pin 7. So that's my pin 7. And so when the pin 7 is connected to ground, this is the behavior. When I connect it to +5, then you see that my LEDs go binary 0, 1, 2, 3, 0, 1, 2, 3, and I can force that machine to stay in that state if I want. I'm going to wait till it switches, and then I'm going to close my switch. So here I have the implementation of this finite state machine, but in software. So let's take a look at the sketch and what that looks like. So that's the finite machine software sketch. I have an integer here. Let's see, what? An integer state that is going to be 0, 1, 2, 3, 0, 1, 2, 3, defines which particular state I'm in. Button, I'm going to have a variable, so pin 7 is going to be my switch. I'm calling it button. And I have two outside LEDs. One is going to be pin 39, the other one is going to be pin 41. So these are digital output pins. So I want, depending on which state I'm in, to activate the LEDs so that they represent the binary numbers. So state 0, the two LEDs will be off. State 1, LED 0 will be on. State 2, LED 1 will be on. And state 3, LED 1 and LED 0 will be on. And I'm doing that through this computation. So look at that, computer scientists, you should be able to figure out why this works. So that's an extra function. We haven't seen that yet. I'm creating my own C function as a helper. I'm going to give it the state, and it's going to turn on the right LEDs. And so for setup, what do I need to do? I need to say that the button is going to be an input with pull-up. I'm going to use the pull-up resistor from the board, less hardware for me. LED 0 is an output. LED 1 is an output. So I'm defining which particular pins my LEDs are going to be connected to. And then in a loop, I'm going to digital read my button to see if it's on or off. And if it's 1, then going back to this diagram right here, you see that if it's 1, I'm switching from one state to the other. So if the switch is 1, I'm going around my finite state machine. Okay, so that's what I'm looking at. So if the value is 1, then the state should be state plus 1 modulo 4, so that if it's 4, it becomes 0 again. So I go 0, 1, 2, 3, 0, 1, 2, 3. So, and whether I've changed the state or not, I'm going to re-initialize my LEDs to represent what state I'm in. So activate state, and then wait for 1 second. So what if I want to make a change to my finite state machine? You see that with the flip-flop implementation, it's very costly. I have to change the equations, I have to remove the hardware, change wires. It's a very lengthy process. The software version of this, I just have to change the program. So the program is just kind of a version of the hardware. So the two, there's interconnection. I can switch from one to the other. Very kind of flexible thing. The logic is the same, the implementation is different. All right. All right, what if I wanted to generate something, a signal that had this particular shape? So here, having just done this exercise with the switch, how could we write a sketch that would that would generate a waveform like this? So I'm not doing pulse width modulation. I'm thinking finite state machine, and I would like to have an Arduino replace a finite state machine and generate a signal that would look like this. So this here is a period of the signal. So I'm going to assume that this is the same value, even though the diagram here is not necessarily accurate. And I'd like maybe for 10 milliseconds for the signal to be high, and then maybe for 30 milliseconds, and then see 20, it's high and it's low, and then it's back to 10, and it's back to 30. So 40 milliseconds would be the period, but every other cycle it's 10 and 30 milliseconds for the waveform, and then every other one is 20 and 20. So what you could do is you could say, well, that's going to be state 1, state 0, state 1, state 0, and I'm oscillating between the two. And so instead of having a switch and looking at a switch, what I can do in my loop is say, all right, whenever I call the loop once, I'm going to be in state 0. And when that loop is done, it's going to change the state so that we're going to be in state 1, and then back to 0, back to 1. And what I will do in my sketch is check. If I'm in state 0, then I'm going to generate a high level for 10 milliseconds and a low level. If I'm in state 1, I'm going to generate a high level for 10 milliseconds, a low level for 30 milliseconds. If the state is 0, I'm going to make it high for 20 milliseconds, low for 20 milliseconds, and then every time change the state. So having a variable that tells me which state I'm in, and then depending on the state, do something different. So that concludes Unit 3, and what we've done here is we've covered how we are going to do analog input and output. So fairly simple, and new devices. So instead of resistors and switches, now we have variables. We have devices such as a potentiometer, which is going to have a resistor that's going to change as a function of mechanically turning the knob or not. And then we can still use LEDs, and we can change their intensity. All right, so this is it for Unit 3.